Hello and welcome to another video. In this video we're going to be working on word search, and in the problem you're given a grid of characters and a string word and you want to return true if this word exists. So, and the way you construct the word is you can go horizontally or vertically. You can't use the same cell more than once and you can't go diagonally. So for A, B, C, C, E, D, it's right here, and so on and so on. So let's say we have this example, and let's say we're looking for this A, B, C, C, E, D thing, right? And also keep in mind the board is small, so that's the other thing that's like making this doable, is these rows and columns are only 6 by 6. So because of that, we can basically just kind of like brute force it. And there's not too many like better ways to do it, I don't think. So essentially what we do is we start at every cell, and then we try to look for the word. So if we have A, B, C, C, E, D, let's make this bigger. We can just keep track of like what index we're on. And the way we do it is we can have a visited set, or you could modify the input in place, either one. Or you could like copy the board and then go through it as well. But basically what you do is you just, like, let's say we start here, we look, is this an A? Like, we keep track of the index we're at, so there would be an index here, and let's say we're here. So we'd say like, okay, is this an A? If it is, let's mark this as visited, like this, and then let's try to go in every single direction that we can. So like up and left would be out of bounds. Then let's say we try to go down. When we go down, we're gonna say like, okay, is this letter in visited? No, it's not. And is it the letter we're looking for? So the letter we're looking for now is a B. No, it's not. So then we don't go there, and then we come over here. And then once again, we check, is it the letter we're looking for? We're looking for the second letter. So yes, it is. We'll mark it as visited. We go in every single direction and so on. So it's basically like a backtracking brute force. And so the idea is you go in every direction and you keep track of where you visited, so you don't like, because what you don't want to have is like, let's say you're looking for like A, B, A, B, A, B, A, B. You can't reuse cells, so you can't like go here, then go here, then go here, and go here. So that's why you want to keep things as visited. So the idea is like you visit, mark visited, then you DFS or backtrack or whatever in every direction, and if you fail, then you unmark at the end. And that's the format you want. And that's basically how you can do it. The code's kind of long, but yeah. So essentially that's the format. And this works. The time complexity is really bad, but because these are very small cells, this is fine. And if there are multiple words instead of one, instead of an index, you would just use like a try. And then you would just recurse into your try. And there's like the word search too is kind of like that idea. But because here there's only one word, we can just like say like, okay, we're looking for this letter next, and so on. So for this A, B, B, C, C, E, D, we'd like mark this as visited, try this wouldn't work, mark this as visited, try this wouldn't work, mark this as visited. Here, this wouldn't work either because we're looking for a C. So then we go over here, then we're looking for an E, none of these are an E, and then we have an E here, mark that as visited, and then this. And then if any one of your like DFS backtrack solutions returns true, you just return true. And that's basically the idea. So let's code it up. It's going to be a lot of code, and I'll go over all of it. So I'm just going to make a bunch of class variables so I don't have to like pass down a billion variables into another function. So we'll use a word and the board and directions. And this is pretty common. So basically, because you can traverse like, if you think about it, like traversing right means your column increases by 1, your row stays the same, and so on. There's kind of only 4 directions, so we're going to make that array of directions. So we're going to say like this is like the row goes up by 1, the column stays the same. You can't go diagonally, so it's either 1, 0, 0, 1, or -1, 0, or 0, -1. This is the directions you can go. Then we'll have a visited. And in Java, because you can't create tuples easily as far as I know. So instead of a visited set, we can just make a visited array. And so we can just make a visited array that's the length, that's the size of this thing. And then every time we mark a cell visited, we'll just take that index and we'll mark it visited. So that's another way to do it. Like instead of a visited set or a cache that's a dictionary, you can also use an array. And it's more performant in a lot of cases. Okay, and then we'll have our rows and columns. So in our actual function, we just have to set a bunch of variables. So we'll say like rows equals board.length, columns equals board 0.length, and word equals word. This board, I think, or no, yeah. So board. And let's see. So then the visited, so we can initialize visited now. So we'll make it a new Boolean array, and then dimensions will be rows and columns. And now we are gonna go through, so as in the picture, we're gonna go through every single one of these locations, and we're gonna call our backtrack function on each one of these. So I think I called it like DFS or something when I did it. So, but it's basically backtrack, same thing. So we're gonna do a nested loop. So for int row equals 0, row is less than rows, and increase, and same thing for column. So just a simple basic nested loop. Then we're going to call this function, and when we call this function, what we want to do is we want to check if it's true. Like if we did find this word, we only need one true, so then we can just return true. So we can say if DFS or backtrack or whatever you want to call it, and we're going to pass in the row and the column of our starting cell. And the index of the word of like the next index we need to look at. So we need to start looking for index 0 to begin with. So this will be 0. So if this is true, return true. And then we're going to write our function to actually do the DFS. So this will be a, I'm not going to worry about like public and private variables and all that stuff. So it'd be a Boolean function because it just returns true or false. And it's going to take a row, a column, and the index of the word, like the index of the character of the word we're looking for. So what I'm going to say is if the index of the character we're looking for is the length of the word, then we like found it, so we can just return true here. There's a bunch of ways you can do this, but this is one of them. So if I equals this dot word length, then we found it and we're good. Okay. Now the next thing you want to do is you want to make sure to handle all of your like failure conditions, and there's a lot. So I'm just going to handle them all here. So if the row is out of bounds, so if it's less than 0 or out of bounds this way, or sorry, if it's over here, if the column is out of bounds, if we've already visited the cell before, you can optimize to like not traverse the visited places, but it doesn't really matter. Yeah, so or if the letter we're on is not the letter we're looking for. So for example, if we start here and we're looking for this letter, then we'll also return false. So there's like a bunch of stuff here, and we'll just handle it all in one spot. You can make a custom function if you want to. So if row is less than 0, or if row equals this rows, or if column is less than 0, or if column equals this columns, or if this is already been visited, or if the character, this is the last one, the character that we're looking for doesn't match up to where we are in the word. Does not equal the one on the board. So this board. And you can probably make this more performant just by passing these down instead of making them all class variables, but it's whatever. The actual like a big O is going to be the same. So if any one of these is like happens, then these are all failure cases, so we just return false here. Now, like I said in the picture, so we want to mark as visited, then we want to backtrack, then we want to unmark. So we'll say this visited row column equals true. Then we want to go in every single direction. This is where this directions is going to be useful. So we can just go through, we can just loop through all of them. So for int array, we can call it like dirs or something. In directions, we're going to try to go in each one of these. And if any one of these returns true, we just return true immediately. So if DFS of row plus direction 0, and this is why it's convenient, because you can basically say, let me just take row plus the first variable and column plus the second variable, and you're going to loop through all of these. And if you had diagonals, you can also include 4 more for diagonals, so you can include like 1, 1, negative 1, 1, and so on. Okay, so this is going to be this is going to be this, and the next letter we're looking for is just the next letter in the word, so just I plus 1. So So if any one of these is true, we can just break immediately and return true. Otherwise, we have to unmark it. So we will go over here, unmark it, because we want to be able to mark it again in the future. And then we have to return false. And that's why this takes a long time, because you have to like mark and unmark, because like you might get to a letter and it might work, but then it doesn't work in this situation. So for example, like let's say we get to a C, like let's say this third C was over here or something. Like this was this C. Well, we would mark it, but then we wouldn't be able to like get the rest of it. So then we'd have to unmark it and then start at another location, which is like here, to make it work. That's kind of the idea. It's just like a brute force DFS where you're marking and unmarking all the time. But you do have to mark it, or what you could do, like I said, instead of marking it visited, you could just manipulate the letter. So you could say like, okay, if I'm here and it's an A, let me just change it to like a pound sign or something. And then when I come back, let me change it to an A. So that works as well. And then you just check, then it'll never like match up again. So there's a bunch of ways to do it. But yeah, and I think that should be it. So kind of a lot, like I said, you can definitely optimize it all over, but this is like the main idea behind it. So let's see what our issues are. Okay. So not a statement. This is this. Okay. All right. So, oh yeah, so when we're done with this loop, we can just return false. Like that means we tried every single start location and none of them worked, so we just return false. All right. And yeah, you can definitely like optimize it a little bit, but it's not a huge deal. And yeah, so it's actually gonna be pretty complicated to come up with the time complexity, so we can try it because there's a lot of steps. Space is a lot easier for sure. So time. So essentially, first thing is we have every single start location, so that's already m by n. Then for every start location, we can mark it visited, and then like worst case scenario, we can go down a path that's like the length of the word. So that actually, sorry, the number of letters we can traverse, it is going to be the length of the word, right? Like, yeah, but it's more than that because we're traversing that in like every direction possible. So I'm honestly not sure exactly what that's going to look like, right? Because like we might traverse over here and almost get the length of the word, and then it might traverse over here and almost get the length of the word. So I feel like it's every starting letter plus like you can revisit the same location multiple times from every starting letter, because like let's say we start here and like maybe we take a path like this. So you see we visited this letter, but then we can also visit it again by going like this way and this way, and you know, like there's like a billion ways. So I think it's like in every letter you can go in 4 directions, right? So like let's say we're here, we can go in 4 directions, and then we can do that times the length of the word, I think is what it is. So it's literally going to be, so it's pretty big, and I think that's roughly it. So it's something like this. I could be wrong. I think it's literally like this. But because the length of the word is pretty small, it's 15. I mean, 4 to the 15 is still not like that small, right? So if we do like 4 to the 15, yeah, this should fail. So it's definitely not like this big. I guess it's not going to be 4 to the 15. It's mostly 3 to the 15, because once you go to a cell, you can't like go back. You like let's say we start here and we go to a cell, then we can't go back. So it's not 4 to the 15. Maybe it's like 3 to the 15. Let's see what that would be. Yeah, so this is now we're getting to like passable territory times the m by n, which is like another 20. So it's kind of close, but yeah, I'd say it's roughly, I'm not going to spend too much time. I'll say it's like roughly this, because yeah, for the first letter you can go in any direction, but for every other letter, since you can't go to where you came from, it's literally going to be like 3 to w. Hopefully I'm correct about that, but it's whatever. Kind of hard to come up with the exact thing. Space is a lot easier. So directions is nothing. The board, like, even if I didn't make a class variable here, it wouldn't matter, because you have to have a visited set. But the space is actually not that bad, because the word is only 15 characters, and the visited set is only, or the visited array is only like 6 by 6. So all these things are tiny. So yeah, this is like technically m by n, but because m and n are like 6, it's tiny. So we'll just say it's like m by n space. And yeah, I think it's gonna be all for this one. So hopefully it's helpful. This is definitely one that is like a core problem. I actually watched someone's like meta interview on YouTube where he went over the questions he got asked, and this was one of them. So definitely this just like core backtracking principle is definitely one I would practice. Very good problem to practice it, especially in like a more verbose language like Java. Like I can show you the Python solution real quick. It's a lot smaller, so definitely in Java this is like trickier in more verbose languages or whatever you're doing. And yeah, good one to practice. So if you did like this video, please like it, and please subscribe to the channel. And I'll see you next one. Thanks for watching.